Unification was invented, I think, in the early 70s. And as often happens, there's a dispute about exactly who invented it. There's a footnote about that in the book. Everybody outside of MIT says it was this guy in France. Everybody at MIT says it was Carl Hewitt at MIT. The reason for the dispute is that Hewitt wrote this enormously long thesis that nobody understands. It's really dense. If you think our textbook is dense, you should see Hewitt's thesis. So it's not clear what he did or didn't invent, unless you read very, very carefully. Anyway, be that as it may, the unification algorithm, all by itself, is Turing complete, meaning anything you can compute with a computer, period, you can compute with this algorithm. So we can have this query system that basically does nothing but unification, and that's all you need to compute any computable function. Okay? When I say computable, the bad news, and you'll learn this if you do automata theory, is that of all the functions that there are in the world, only a teeny, teeny sliver are computable. It's infinite. There's an infinite number of computable functions. But there are degrees of infinity, and this is a teeny one. There's way, way more functions that aren't computable. But if it's computable at all, that's the sense in which I'm saying that this is universal. Any function that's computable at all is computable this way. So that's what makes logic programming interesting, is the fact that it's universal. And people didn't realize it was universal until the unification algorithm came along. So you're going to read about it in the book. You're not going to try to remember how it works, but you're just going to see, boy, they sure have to deal with a lot of special cases to get this right. So the result is beautiful and elegant above the abstraction barrier when we do logic programming, but the algorithm itself is messy. OK, so that's the story on unification. So when we see a rule, we unify your query against the conclusion of the rule. If that works, the result is an extended frame, right, because we had some bindings in the course of doing this unification, and a new query, namely the body of the rule, in which case it's that and. So we're going to take and parent blah, 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 parent blah, 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 and we're going to try to evaluate, to Q-eval that, starting here, starting with these bindings. So old one and young one are constrained. Well, old one isn't really constrained. What's really going to happen is later on we're going to constrain old one, and that will implicitly constrain who to have a particular value. Young one, we know the value already, and it's got to be that to match. So we're going to end up looking for everybody who's a parent of Brian in the assertions. OK. That's an and, that body. And is special. Remember I said and, or, and not are kind of like the special forms of the query system. So we don't try to find a rule whose conclusion is and blah, blah, blah. We don't do that. Instead, we take all the pieces, and there could be, you know, in this case there's exactly 2, but there could be any number. But I'm showing you how 2 works, and you can see the obvious extension to more. And we're going to see how and or and not are evaluated. So starting with and, what I've drawn here is the initial situation when you're typing a query at the query prompt. Namely, we start with a stream. That's what these braces mean. And inside the stream is an empty frame. Now, that's not what's going to happen here. Because in this situation, this and is the body of a rule. So what's going to come in here is a stream that includes this frame. And maybe some more frames if there are more matches to other rules. Probably there aren't. But so there's going to be at least this frame where I've drawn this empty stream, this stream with an empty frame. So This is just to remind you what the initial conditions look like, but what's coming in here can be any stream of frames. And we want to evaluate and PQ. And I think this is one of the most beautiful things in the course. It's up there with tree map. Not quite, but almost. We take whatever our initial stream of frames is, we query evaluate P, the first piece of the AND. The result of that is a new stream of frames, which we use as the input to a Q eval that evaluates Q. Because what's going to come out of here is every possible way to match P, every set of bindings that makes P true. And then, starting with those bindings, we're going to look for ones that also make Q true. And that's what's going to come out the side here. So when you sort of cascade Q eval calls one after another in this way, you're computing an AND. Isn't that beautiful? Yeah? And one thumb up. Okay, a few people like it. I love it. I don't like OR so much. I mean, it's okay, but it's not mind-blowing like AND. Because what we're going to do is evaluate P and Q independently. Because for OR, you don't have to have one set of bindings that satisfies both of them. You're going to take any set of bindings that satisfies either of them. If it satisfies both, that's a bonus. If it satisfies both of them, you might end up with the same result printed twice. Because it means there's two ways to deduce the same set of bindings, the same frame. Okay? So starting with whatever we're starting with in both cases, it's the current environment stream goes into both Q evals. We evaluate P, we evaluate Q. Each of those gives us a stream of frames. And now we have to somehow merge this stream of frames. How do you merge two streams? Yeah, interleave. This is why when you do a query that's at all complicated, you're sometimes surprised by the order in which the results come out. It might look a little messy. Why? Because what you're seeing is the result of an interleave. And, you know, that gets a little messy. So that's the explanation for that.